Hello, my name is Dennis. I'm team lead at GlobalLogic. And today in this video, I will try to show you how it is to be an embedded developer. What do you need to become a quite good embedded software engineer? My personal opinion that the best way to explain this is to implement a quite simple and small project from the beginning to the final demonstration. And in this video, I will guide you through all the process. And after the video, we will talk a little bit about what do you need to become a quite good embedded software engineer. And you will ask yourself, do you really want to be an embedded engineer or not? So we can start. The main idea of our project is to implement simple slide meter application. We will use STM411 discovery board from STM company, like a basement for our project. We will connect photo detector. Actually, this is the photo transistor that will help us to measure amount of light that we have that is falling down onto the detector. And we will divide this amount of light into three regions, like big amount of light, medium amount of light, and small amount of light. So photodetector will be connected to the discovery board, and we will get results from the photodetector with help of it. Additionally, we will connect three color LEDs. Actually, this is the three LEDs in one single package. And this device also would be connected to our board. And we will use it to indicate how big amount of light we have. In case if we have big amount of light, we will enable green LED. In case of medium amount of light, we will indicate it with help of the blue LED. And for the small amount of light, we will indicate this with help of the red light. Project is quite simple, and implementation would not take so long. Please treat this like a proof of concept project. This is not the commercial project. And this is only to show you how it looks. Do not use it in commercial development. I warn you. So let's start with the LED first. Right now we have a three-color LED. You can see it at the left side of your screen. It's constructed like a three LEDs in one. We have three LEDs of different colors, red, green, and blue, in one single package. And we control them independently, one from each other. The main trouble for me right now is to understand what type of the connection we have. As you can see from the screen on the right, we have two possible combinations: common cathode and common anode connection. Which one we have right now, actually I don't know, and we will find out a little bit later. This is really important for us to understand how it's connected to write program right. Because without this information, we cannot create program at all. So you need to understand what type of the connection we have. And this is what we will find out right now. So let's try to check what LED type we have, common anode or common cathode. For this stuff, I will use simple multimeter. I will enable continuity check mode. This one, it's when you are checking the connection is present or not. If connection is present, you will hear the sound like this. I will connect two connectors, black and red, and you will see the light is blinking here, and you will hear the sound that connection is present. It's really simple and important function of the multimeter, and it will help us to understand what type of the LED we have right now. Let's start with the simple action. I will apply negative output of multimeter to the common pin of the LEDs. It's here. And after that, I will try to apply positive to the pins which connected to the proper colors. And actually, we can see that nothing happens. It means that this common pin is not negative. It should be positive. At least I hope so. Let's try. Let's try do the opposite. I will apply positive pin to the common, and negative pin I will apply to the colors. Green, magic. You see the green color here. Red and blue. So we have found out that we have common anode. Construction of this LED. So you need to apply a positive voltage here and negative voltage to the proper line, green, red, or blue, to get the color from the LED. And this mechanism help you to understand where the common pin actually is. If you don't have any information about this LED, you can try different combinations, and sooner or later you will find out which pin is common. It's common anode, common cathode, in which pin represent each color. Something like this. So let's look closer on the three-color LED that we have right now. It has 3 crystals in one single package. 3 main colors, green, red, and blue. And we can control each color independently. Enable, disable, and even control intensity of the color light. Let's try to do this. We can enable green light right now. So only the green crystal is working right now. Red and blue, they are turned off. So right now we can enable only the green light. and only the blue light. Of course, we can enable them simultaneously, like this. Here we enabled red and green light, and as a result, you will get the yellow color. That's how physics works. Let's enable different combination. Right now, this is the red and blue, and you will get the violet, as you can see. And the third one combination of two that we have, it's green and blue. If you will enable like this, you will get a teal color. And of course, if you will enable all three crystals at the same time, like this, you will get the white color. This is really cool stuff. This is really cool LED that we have right now. And the coolest thing that we have right now, that you can control intensity of each crystal. So more green or more blue in compare with other colors. And this way you can generate any color you like with help of your microcontroller, with help of your program and that you will create for your microcontroller. Let's check what we have, like a photo detector. In our case, we have photo transistor. You can see it here. This element will change its internal resistance depending on the external light is present or not. To show you how it's working, I'm connected it to the multimeter. Multimeter is working like a measurement of the resistance. And right now we have internal resistance of this element, something really close to 16 kilo ohms with this current lightning. If I will turn light on, as you can see, internal resistance of this element will grow up. When I will provide more light to this element, internal resistance of this element will be lower. That's how it's working. We will provide voltage, ground to this element, and we will get an output in form of voltage. And this output we will measure with help of our microcontroller. Now it's time to check the schematics. Schematics is a really important document, especially in domain field. It will show you which external components you have, how they are connected one to each other, and with help of this document you can understand how to create your program, how to manipulate with all your components right. Let's see what we have and what I'm talking about. We have a 3-color LED component. It's present here. And as you know, we have the 3-color LED with common anode. This anode line would be connected to the 3.3 volts. We will provide voltage from the STM board. So positive voltage here. It means that if we want to enable respective LED, we need to create negative voltage here, 0 in our case. Red LED connected to the port A1, green LED connected to the port A2, and the blue LED connected to the port A3. With help of these 3 pins, providing 0 or VDD voltage levels here, we can enable and disable these red, green, and blue lights. If we will provide 0, current will flow and the LED will turn on. If we will provide VDD, 3 volts here, no voltage difference would be present. It means that no current flow and the light would be turned off. Everything is quite simple. By the way, one small note, I would not use series resistance here. And because, according to my measurements, of course, we don't have huge currents here. For the red, we have something like less than 10 milliamperes. For the green, something close to the 4 milliamperes. And for the blue, we have a 2 milliamperes. Those current are sufficient for our microcontroller, according to the documentation. That's why, to simplify my own life, I just skip this series resistance in our case and connect directly. But this is the not really common use case, and this is not really good. So in commercial projects, please apply series resistance, of course. Okay, we understand how we can control our LED, and let's analyze photodetector. Here we have photo transistor. You know, this element act like a resistor that will change its internal resistance depending on illuminance, depending on light, absorbed light. If it have big amount of light, its internal resistance would be low. If it will have not so big amount of light, so it will be dark, internal resistance will increase. And knowing this information, we can analyze and read output from this small board. We will apply voltage here, ground line here, and we will have the third line. Actually, it's output from this photo transistor to our board, to our discovery board. And according to my measurements with help of multimeter, we will have something in between. 0.1 volts we will have for the dark scenario, and 0.9 volts we will have if we will apply light. And knowing this information, we can start develop our own code. We will configure this line like analog input, and with help of internal module of our microcontroller, analog to digital converter, we will check what voltage we have and act accordingly. And with help of these 3 pins, port A1, port A2, port A3, we will configure them like a digital outputs, and we can control our 3-color LED. We will enable and disable appropriate crystals. So all prerequisites are gone, and we are ready to start our software development. Let's go to the next session. So we're almost ready to start our development. Just two more things that we need to have before we will be ready to make our own project. First of all, we need to have a schematic for sure. And actually we have it. I will try to show you. Our schematic. It's quite simple. We have three colors: LED with common anode, and we have a photodetector, phototransistor. To configure our three-color LED, we need to configure outputs port A1, port A2, port A3, like a GPIO output, and we will be able to control the LED. For the port A4, we will configure it like an analog input, and with help of analog to digital converter, we will read digital value from the photodetector. So again, schematic, it's really important document. Without it, you cannot create your own code, right? And regarding the photodetector output, it provides a voltage between 0.1 volts to 0.9 volts. I checked those values with help of my multimeter. And I have prepared table to have a reference values to create my program. Let's do it. Let's see it. The main signal for our photodetector is light. Big amount of light or medium amount of light or small amount of light. So I don't have an actual photometer. That's why I just put some subjective marks here, like low amount of light, high amount of light. Light with help of phototransistor would be transferred to the resistance. Actually, phototransistor have its own internal resistance, and if we will provide low amount of light to this phototransistor, it will have high internal resistance. If we will provide more light to the photoresistor, internal resistance of the phototransistor will become lower. So more light, lower resistance. This is how it works. This is the physics of the phototransistor. After the phototransistor, like an output from the phototransistor from this board, we will have a voltage. 0.1 volts will indicate that we have really small amount of light, and 0.9 volts will indicate that we will have more than enough light. Sounds like this. And I divided this range into three groups. For the small amount of light, we will turn on red light in our LED, three-color LED. For the medium amount of light, we will enable the blue LED, like indication. And if light more than enough, we'll enable the green light. Sounds like this. Voltage would be measured by analog to digital converter inside our microcontroller, and the microcontroller will provide digit which corresponds to the voltage that we have on a particular pin. So voltage would be transferred to the digit with help of analog to digital conversion. And I have recalculated voltage to the digit values here. So this would be our reference values that we will use to create our program. So all prerequisites are gone. We can start our STM32 IDE and create our program. Let's do it. Let's run our STM32 Cube IDE. And create a new project. First of all, we need to identify the microcontroller that would be used in our case. This microcontroller present on the development board. And we need to select project name. Let's call it Light Matter. This is not commercial project. This is like a proof of concept, educational, simple project. Please don't wait anything extraordinary here. First thing we need to do is to configure our peripheral devices. Inside the microcontroller, we will use general purpose input-output port pins, those one, port A1, port A2, port A3. For the green, red, and blue LEDs. And we will use this pin port A4 for the detector connection. To configure all these things right, we need to check the schematic first. Let's do it. Again, port A1 responsible for the red LED, port A2 for the green, port A3 for the blue. It means that we need to configure those pins like general purpose input-output pins. Port A1 GPIO output, port A2 GPIO output, and port A3 GPIO output. That's all regarding the LED. Let's see what we have for the photo detector. Photo detector connected to the port A4 pin. We need to configure it like analog input. And we will use analog to digital converter to read voltage present on this pin. This is the pin that we have, and we will configure it like ADC in 4. That's all. Basic configuration is done. We will save our project and move on to the source code tab. Steam IDE will create configuration and will create a program skeleton for you. Here you can see the main function, basic initialization stuff for the GPIO and ADC. And we will have the while loop, internal while loop, endless while loop. It's common use case for whole embedded projects. And we will create all our code here. This code would be really simple. Let's do it. First of all, we need to start analog to digital converter. So it will start conversion voltage to the digit value, to the digital value. How it can be done? With help of the hardware abstraction layer, ADC start function, and we need to provide instance, ADC instance that would be used. Instance number 1 in case. Conversion is started, IDC starting to make conversion, and sooner or later we will get the result. And next command would be responsible for waiting of the conversion end. This is a pull conversion command. Actually, what it's doing, it's waiting for the conversion end, where we will stuck there until the end of ADC conversion. It's like pooling mode. We will use pooling mode in this simple application. Again, we need to provide handle for the ADC. We need to provide timeout value, 5 milliseconds. 5 milliseconds, it's more than enough for conversion to be completed. 5 milliseconds timeout. If conversion would not be completed in 5 milliseconds, it means that something is wrong in our case. But it will be completed much more faster. After the conversion is completed, we need to read the value from the ADC, from the analog to digital converter. And for this stuff, we need a variable that would be used to get the result from it. Unsigned int 32 bits value. We will call it v, and this variable will get result from the ADC with help of how ADC get value command. Again, we need to provide handle for the ADC. That's all. Quite simple. Starting the analog to digital conversion, waiting till it completed, and get result. After this, we need to enable disable LEDs according to the value that we have inside this variable. Let's do it with the simple if statement. If variable v is less than what the reference value we should have, let's go back to the table. We have a special table for this. This value we will have in the v variable. And let's do it like this. If we have a value lower than 372, we will enable red light. V is lower than 372. We need to enable red light. Again, hardware abstraction layer, GPIO, write in function. Now we need to provide a port that we will use. Port A, pin number, GPIO pin number 1, responsible for the red LED. And we need to provide a proper state for this pin. Which state? Pin have two states, low state and high state. It means it would be logical 0, logical 1. In terms of volts, it would be 0 volts or 3.3 volts. And we need to provide proper voltage to enable the red LED. Let's come back to the schematics. This pin, we are actually changing this pin right now. From the anode side, we have a high state, 3.3 volts. It means that to enable this LED, we need to make a current flow through it. It means that here we need to have a low state, 0 volts. High state from cathode, from anode, a low state from cathode, and the current will flow through the LED and LED will turn on. Quite simple. And we need to set it to the GPIO in reset. It will move this pin to the low state, to the 0. And the red light will turn on. Rest of the LEDs should be turned off. It means that pin number 2 and 3, pin number 2 and 3 should be moved to the high state. If we will have high state here and high state here, it means that no voltage difference present between cathode and anode, and no current flow appears through the green or blue LED, and they will be turned off. Quite simple. First block is ready. It's for the green or the red LED. Let's write use case for the blue LED. If V is lower than, let's move back to the table. If V is lower than 745, we will enable the blue LED. This block. We are writing the code for this block, for this value, for this values, for this range. And we will enable the blue LED, and red and green should be turned off. Let's do it. Red LED present on the pin number 1, we will disable it. And the blue LED present, sorry, wrong block. We need to put it here and modify it here. 745 here. Red LED should be turned off, and the blue LED should be turned on. Where the blue LED is present, pin number 2 or pin number 3? I don't remember. We need to check the schematic first. Let's do it. Blue LED present on the pin port A3 here. Okay, pin number 3, blue LED here, and we will enable it. So the second use case have been covered, and we need to write the code for the last use case. The last one, when the values is bigger than 745, we will enable the green LED. Else use case will cover this scenario. Green LED present on port A2, and we need to enable, move it to the low state. Port A1 and port A3 we will move to the high state. Let's do it. Port A1 would be in high state. Port A2 we will move to the low state. That's all. Let's check we can compile the project or not. We have a one error. Typo error here. Now it should work fine. Yeah. Build succeed. Zero error, zero warnings. Now we can flash our program to the microcontroller and check how it's working with help of the actual hardware. We can do it from this ADE. Run command here. No recent launches. Means that we'll need to create a first configuration. Sometimes this application had this issue. We just need to open this configuration, change nothing, and initiate run command. As you can see from the log, flashing in progress. Erasing, downloading, verifying, download, verified successfully. So our program had been flashed to our microcontroller, and we can check what results we have in practice. Let's move on to the next section and check the actual result. We are ready for the demonstration phase. As you can see, we have a photo detector here for the transistor. And actually, right now, we have a condition when we have quite big amount of light detected by it. This can be seen by our LED. We have a green color right now. It means that amount of light is quite big. Let's try to reduce amount of light falling onto this photodetector. I will use a simple white paper and we'll try to make appropriate shadow on our photo detector. When shadow falling onto photo detector, as you can see, we have a blue color of the LED. This is the middle range that we have, and not so big amount of light, but not so really small, somewhere in between. And now we need to check the use case when we have not so big amount of light, actually small amount of light. I will use metallic ruler for this stuff to generate quite strong shadow. Let's try to do this. Right now we have situation when a really small amount of light falling down onto the phototransistor. That's why red LED is turned on. So our program working as expected. We have checked this situation with actual hardware, with actual lighting, and this is quite good. One more thing I can do for you. It's dark outside, and I can turn off my headlamp, my desktop lamp. So you can see that right now we have a green color of the LED. Now I will turn the light off. And you can see that red LED is turned on because no light present. I will turn on my desktop lamp again, and you can see that LED color have been changed to the green. So everything working quite good, and this is really cool. So we have come to the end of our video. Like it was agreed before that I will tell you what you need to do to be a good embedded engineer. Basically, you need to have a good knowledge from the school. I'm talking about math, physics, electronics, and English language. This is the basement for whole programming stuff in embedded domain, especially. Regarding the programming languages, C and C++ are widely used. They are commercial standard. You should know them really good. Additionally, you should know Python. It's also widely used, especially if you need to create some kind of scripts or fix the scripts that are already created by other developers. So, yeah, you should know it. Additionally, you should have a handicraft experience. I'm talking about soldering. From time to time, you need to fix some things. You need to fix or solder workarounds for the customer hardware, or you need to create your own device and you need to check is it possible or not, like implementing proof of concept project. So soldering must have. You need to have an experience to work with multimeter and be able to work measure current, voltage, resistance, and understand the difference between them. You need to have an experience to work with a oscilloscope, and especially if you work with some kind of devices that communicate with each other, you need to have an experience working with logic analyzers. It's a really cool device, especially if you need to create your own communication protocol or debug some kind of proprietary commercial protocol that you are not aware how it's working. Additionally, beside all this stuff, you need to have a domain knowledge. Embedded, it's quite big area, and it have subdomains. Some of our guys working in automotive domain. They making a project somehow connected with the cars. Other guys working in networking domain. They working with switches, routers, and other networking stuff. Other guys working in medical domain, Internet of the Things, avia, military, or other domains are possible. So each domain have its own tips and tricks, knowledge that you should know to be a good embedded engineer. Additionally, you should have a good software skills. Soft skills. I'm talking about communication with the other team members, communication with customer, especially if customer is not in your country, if he is a foreigner, you need to know how to speak right with your customer, with other colleagues from other countries. How to do it right. And if you want to become a software engineer, embedded engineer, try to implement your own pet projects. Quite simple, but connected with domain that you will like to learn. Implement it from the beginning to the end. It could be really small, but it should be something interesting. Something should blink, make a sound, make a noise, move somehow. Try to make fun of it. And of course, don't forget to put your code on GitHub. The most important thing regarding the domain and regarding the software development, you should like your job. If you like your job, everything rest would be completely fine. So I wish you good luck and see you later. Bye bye.